So with this, maybe I can get started with the introduction of the speakers today. So we have Utkarsh he's a postdoc at Carnegie Mellon University, CMU. He's going to talk about, do vision models develop human-like progressive difficulty understanding? And then we also have Alessandro from University of Trento on large multimodal models as open world image classifiers. They sound super interesting. So, Utkarsh, would you like to get started?
Yeah, sounds good. Let me just share my screen.
So you have 10 minutes each,
Okay.
roughly. Yeah.
Um, can you guys see the screen that I'm sharing?
Yes.
All right. Yeah, so I thought of just sharing directly the paper because like most of the
Cool. Yeah,
just
that's what we try to do. Yeah.
yeah. And so uh, yeah, so in this paper we were trying to understand whether the image classification systems that we have do they possess one specific ability that humans have, which is that we learn concepts in a progressive manner. So what I mean by that is, let's say you're trying to learn mathematics for the first time. Like you give some students a test, and you have two different types of questions. One is 2 times 3, and the other is 2 times 3 times 4. Now, all of us can intuitively understand that if someone gets uh, 2 times 3 times 4 correct, they will very, very, very likely get 2 times 3 correct as well, right? And conversely, if someone does not get 2 times 3 correct, they won't get 2 times 3 times 4 correct as well. What this means is that we can only, as humans, only solve harder questions if we can solve the corresponding easier questions first. And if we cannot solve the easier questions first, we won't be able to solve the harder questions. That's normally how all of us learn. And if this thing does not happen, then you would actually start to question. Like for example, if I can actually answer 2 times 3 times 4, but I can't answer 2 times 3, then you actually start to question whether I've just memorized 2 times 3 times 4, right? And versus whether I've actually learned the concepts of multiplication. So we wanted to do that. We wanted to test whether image classification systems actually have this ability as well. Uh, so what we then do is we actually try to create these kinds of easy, medium, hard concepts for a particular class. So we consider image classification. That's what we work on, and that's where we want to test this phenomenon. And I'll explain in a bit how we actually create these easy, medium, hard examples. But for now, just imagine that there is a category of golden retriever. That's the object class. And within this object class, if you imagine occlusion as an attribute, then we can understand that in this figure on the left side, the leftmost image, it is the easiest one because there is no occlusion. The dog is completely visible. The middle one is kind of somewhat difficult because the dog, most of the body is still visible, but some parts of it are occluded behind this bench. And then the last one is maybe most difficult because most of the body of the dog is occluded by these leaves and only the face is visible. So if we imagine these three images, these three questions, so to speak, for the model, they're easy, medium, and hard. Like it's most difficult to get the last image, which is the rightmost image, correctly classified as golden retriever, according to us humans. So now, if the principle that I just described, which is how humans learn, if that is how models like the visual recognition models also learn, then what we propose is that there should be there should be a certain behavior that we should expect in the model's responses. So on this right hand side, what I'm drawing are all the possible scenarios whether the model gets um, an image correctly classified or incorrectly classified. Correctly classified means green, and incorrectly classified means red. So you can see, like if you see my cursor over here, all the images are correctly classified. The first two are correctly classified, and then similarly, all are incorrectly classified, and all the other combinations in between. And what we say is that if visual recognition models actually have that same ability that humans have, then most of their responses should actually fall into these four categories out of these eight possibilities, which I've highlighted in these red boxes. So it's actually perfectly fine if the model just does not know anything, which is this case over here. So it gets all the images incorrectly classified. What is weird is if it gets just the hard image classified correctly, but the medium and easy image incorrectly classified. That is this image. So again, like the hypothesis that you want to test is whether um, certain popular visual models that we currently have, that we currently use, whether their responses actually indeed fall under these four out of these eight possible categories. That's the hypothesis that we want to test, right? And Yeah, so that's our central thesis in a sense. And then based on whether this is true or not, we can actually think of some applications for these models. And essentially, I can just explain, give some examples of what these easy, medium, hard examples look like for other attributes. So again, considering the same object category, which is golden retriever, you can imagine different kinds of difficulties. So if you imagine lighting as the attribute, then um, you can see that this is how the easy, medium, hard can look like. Like the leftmost image is kind of easy because the lighting is just perfect. The middle image is kind of in the middle because like there is some shadow, so it's the texture details are not that visible. And then the last image is most difficult because it's just the like the shadow or like just the outline of the dog without us knowing the color details. And then similarly, we can actually create such examples for different kinds of attributes within a particular object category. So occlusion we already saw, and then viewpoint is one of them. So the first part of our paper was actually designing such a data set, which can have this kind of labeled information, right? Because um, the problem is that normal image data sets, we don't really have this information. So what we do is we make use of these generative models, and particularly some large language models and generative models combination to create such a data set in which we can visibly see such progressive increasing of difficulty. And this figure just illustrates what the process looks like. So we first start with some class names. So we take 100 classes from ImageNet. For each class, you know, basically, and then what we ask GPT is to just give us some set of attributes that describe certain image variations within each of these classes. So it outputs, okay, occlusion is one thing in which things could be different, quality, size, viewpoint, etc., etc. Then for each class and for each attribute, right, we ask it to generate some certain attribute values. So if the occlusion has to be in an easy mode, what should be the textual description of the occlusion? And then basically what that means is it should be no occlusion or object is fully visible. And if it's hard, then maybe the text description could be majority of object occluded. Once we have these attribute values, we actually generate the image prompts. So the class name, the attribute type, and the attribute value, all of that is used to create image prompts for easy, medium, and hard images. So a golden retriever standing in a sunny green park, fully visible with no occlusion, smiling. So that's an easy prompt for the golden retriever and occlusion attribute. And these are the images that we already saw. So once we have this kind of images where we have like a labeled information for easy, medium, hard, what we then do is we actually then simply test many of the image classification models on yeah, what are the different types of responses that they have in a sense. So if you, in this figure, what we are seeing is that, okay, for ImageNet, ResNet, so a ResNet 101 trained on ImageNet dataset, most of the responses are like, you know, on this x axis, we are showing what the distribution, what is the order of its responses for easy, medium, hard over here. And what we see actually is that for most of them, the majority classes do indeed actually correspond to the four classes that I talked about. So it never, what that means is it very rarely gets something like this, if you see my cursor, where the hard one is correct, but the two medium ones or easy ones are incorrect in a sense. And the key finding is that if you simply measure the hierarchical, if you try to quantify this behavior into some score. And the way we define that is, what is the percentage of responses which fall under these four categories that match human learning principle? It is actually very high. Like it's more than 80% for all the models that we test. If, like this bar graph over here. That was the first takeaway. And using this, sorry, just out of just for the sake of time, so that's an observation that we find based on our experiments. And the other thing that we wanted to test was that, okay, given that models actually learn in this way, can we use it for some good purpose in a sense? And what we thought was that, humans, like the way GRE works, this is standard testing, it's actually dynamic. So you don't test a human subject on all the questions. You first start with some sample set, and then based on how the human is doing, you make the test progressively more easier or progressively more difficult. The idea is that if a human is getting the hard question correct, you don't need to test the human on easy questions. So similarly, we designed an analogous GRE test for visual recognition models, in which instead of testing the model on all the possible images of easy, medium, hard, we start with some medium, average distribution of questions. So one easy, one two medium, one hard question. And based on how the model actually does, based on how much score it gets, we assign some score for getting each question right or wrong. Um, Hard questions have more points. um, so based on how it does, we progressively change the next questions that it faces in the next round. So based on the score 0 to 9, um, the distribution of the next round of questions will be different in a sense. And what we find is that, if you actually evaluate the model in this way, where you don't actually need to test the model on more hard questions if it's not getting easy questions correct, you can actually very reliably estimate how well it would have done if you had tested it on all the questions, easy, medium, hard. So just in very summary, what this means is, um, if you um, like the error between ours versus a baseline in which we're only testing it on same number of easy, medium, hard is much lower over here. So this is basically denoting that error, which is like lower than like the baseline, which would have been if you had not done this dynamic testing in a sense. I think that that's all that I maybe mostly wanted to talk about. I think the main takeaway is that they do indeed have this property, which till this point had not been explored. And we do think that this is something. It's another way of testing generalization ability of these models in a sense. Yeah.
Yeah, thanks for sharing your work. It's
Yeah.
super interesting. If there is any quick question for Utkarsh, please go ahead. Otherwise, if there is some long discussion, we try to push that to the end of the session. Okay, so otherwise we can move to the next speaker, Alessandro. Would you like to share your screen and get started?
Yeah, I'm trying. I just say like everything is set to unknown, so application. So let me just general like
Ooh, okay.
sharing issues when I when it's my turn. So let me see if I manage to. Yeah, so I see all of my applications as like warnings, and I, like for all the windows I can select from to share.
Oh, okay. So you can still share something, but somehow
No,
you
I think I
select
can share, but I don't know what I'm sharing basically.
Okay, okay.
So I can try and see what happens.
Yeah, just
Okay,
try
let me
it.
see.
Yes. Hopefully
So
it's
it's
the right window.
permission issue then. I have to quit and reopen. Is it fine? It just take like
Yeah,
30
just do
seconds.
it. Yeah.
Okay. Thank you. I'm
Well,
sorry.
we'll talk about maybe Utkarsh's work in the meantime. Um, so I was wondering, so you set the difficulty by generating those images. Um, yeah, I'm just wondering if people will agree with because difficulty is also kind of subjective.
Yeah.
So
Um,
what do you think?
so yes, what we have done some user studies as well regarding this. But yeah, for the most part, as you said, it's since by definition it is supposed to be subjective.
Mhm.
The best way we thought of addressing that will be just show lots and lots of examples in the supplementary of like the easy, medium, hard,
Okay.
and just have the people just see for themselves what do you think. In a sense, we do think in the most cases, it is like the generative models, they are following the prompts correctly, and it does make a logical sense why one image should be more difficult for a human as well. But yeah, we have done some user studies as well just to get there.
And yeah, maybe one more question. So maybe is the question asked that the user study more like self-judgment of how hard it is, or is it more like asking humans to do the classification itself?
No, it's basically, so the way we had conducted study was that in each session, like the user will just get images of the same class, like golden retriever, and it will have two images. And it has to select which one is more harder to classify as golden retriever. So it could be easy medium, it could be easy hard, it could be medium hard, so all kinds of
I see,
combinations.
yeah.
So
Ah,
throughout the
interesting,
user
yeah.
study, you'll have an idea of whether they're actually choosing the more difficult one or not. Uh, yeah.
Okay. So in the meantime, Alessandro has joined again, and yeah, the sharing is working.
Okay, nice. First problem
Things are
solved.
ready to go.
Nice. So I made slides.
Cool.
I mean, first of all, thank you for inviting me. It's a pleasure to be here and present my work. And the presentation is, as was already said before, my latest preprint on large multimodal models as open world image classifiers. So the outline of the presentation is about large multimodal models applied specifically for image classification. And the main 2 points we will discuss is why we do this and also how we do this, with more focus on the second part. So, I mean, the reasons for why we decided to evaluate large multimodal models for image classification as like four main points. I mean, first of all, no one did this before, so it was like an open research question we wanted to answer. Second point is that these generative models, so these large multimodal models, which are language models with a vision encoder to encode images, enables generate work by generation, and so enables open world classification. So working without any prior on the list of class names. The third point is that actually classification is pretty useful in a lot of different pipelines and applications. More so that it happens sometimes that, at least for my personal experience, I find it more helpful to have a model that is able to classify what's in front of me, maybe like for fine-grained classification, rather than, for instance, I don't know, like solving a math equation by like inputting the image directly. And the last reason for why we wanted to focus on this was that we also researched prior to this what we termed vocabulary-free image classification, which was our attempt to make CLIP, so a contrastive language image pre-trained model, work on the open world without any prior knowledge on the list of available vocabularies that we may care about identifying. So about the how, we have four main points. The first two are about the models and datasets and also the metrics we had to define to quantify the performance of these models in open world. And the second half of the how is about the mistakes these models makes and also how we can solve these mistakes. So very briefly, like we decided to focus on 7 open source families of large multimodal models with 13 different instances. So which may span different billions of parameters. So for instance, Chuan 2.5, Chuan with 2 billion parameter, or Chuan with like 7 billion parameters. We also decided to focus on 10 different image classification datasets, which we grouped in 4 categories, spanning from what we refer to as prototypical image classification, so traditional object recognition, for instance. So think about Caltech 101 as a dataset, to what we termed as non-prototypical, so classification with classes that are not very, let's say, common, so like textures, maybe verbs, or also satellite imaging. And then we had two groups about fine-grained, so for instance, food, and very fine-grained, which is instead about, for instance, car brands or aircraft brands. And in this setting of open world, we had as a reference for the performance of these models CLIP as an upper bound with, of course, the list of ground truth labels for each of the datasets. In terms of the metrics, we couldn't actually directly apply accuracy because, of course, we don't have a list from which to select the prediction from. And also predictions from these models are generally free-form. So it's like comparing a sentence against a single word, which is the label for the image. Another problem in using accuracy itself and also for defining the metrics we wanted we needed for the problem is that language is generally ambiguous. So it could happen that, for instance, a generative model may propose the label sofa while the ground truth is couch, for instance. And in this case, of course, we would like to keep consider the prediction as correct as they work as synonyms. So for this, we decided to work on two types of metrics, which are inclusion and similarity. For inclusion, we resort to standard textual inclusion as a, let's say, starting point, which simply evaluates if the ground truth label for the image is present in the generated text, so the answer of the model. For the second, instead, we resorted to using a language model that was comparing the prediction of the model, so the text, against the ground truth label. And this was needed because, as for the example of before, language is ambiguous. So if we were to compare, this is a photo of a couch against the label sofa, it wouldn't work for textual inclusion. For similarity metrics, instead, what we focus on is using textual encoders to encode both the generation and the ground truth label and quantify how they are similar by cosine similarity in the embedding space. For this, we focus first on evaluating the sentence to label similarity, but also we noticed that there is this issue of having very long predictions compared against the label, which results in having generally lower similarity scores since we compare very long sentences against generally a single word. So for this, we propose also evaluating the similarity at a concept level, which simply consists of extracting all of the concepts from the generation, comparing each of them against the label, and selecting the one that maximizes the similarity. And these are roughly the results we got for the 13 models we tested for the 4 metrics we used. As you can see, we have the blue bars are these models, which span from like IDFX 8 billion to Chuan 2VL 7 billion across the 4 different metrics. As a reference, we have as a dashed line the clip upper bound, so using clip with the list of ground truth labels. And also we report 2 baselines taken from, let's say, vocabulary free, or generally simply using clip and performing retrieval instead of generation for the predictions. So basically we treat the problem as image to text generation, retrieval. What you can see from this is that for textual inclusion, of course, as we said before, since it's very strict, performance is generally very low, and the gap against clip is very high. However, when you resort to instead using LLM as a judge, so llama inclusion for the problem, you can see that performance, of course, gets higher in general. While it's also interesting to see that overall, it's the ranking between the different models is roughly preserved. While instead for semantic similarity, you can see again a similar trend where resorting to semantic similarity or sentence similarity, so comparing the entire sentence against the single label results in slightly lower performance compared to when we just check the concepts against the ground truth. I think the most interesting part about this is not these numbers itself, is that we noticed that by combining the metrics we propose, we can actually categorize either the mistakes or more generally the predictions of these models. Indeed, inclusion can work as a proxy to understand whether or not a prediction is correct or wrong, and the similarity can be useful to understand whether or not the prediction is specific or generic. So with this, we identify 4 different prediction groups. The first one is correct and specific, so high scores for both the inclusion and the similarity, which, for instance, could result in having the prediction pug for the ground truth pug dog. Second one is still correct, but more generic. So in this case, for instance, the model may say dog and the ground truth is Labrador, which is technically not wrong as a prediction, but it's not maybe as much as specific as we would like it to be. And then we have the wrong predictions, which instead have a low llama inclusion score and could result, for instance, in predicting Siamese for a type of cat instead of Persian. And you can refer of this as being basically a misclassification, fine-grained misclassification more specifically. And then the last type of prediction we identify is wrong and generic, which simply consists of maybe the model focus on something still in the image, but not related to the label of the image. So for instance, plate when the image contains a tiramisu. Here are a couple of qualitative examples of this. So you can see, for instance, in the first case, we have one image from Food 101 with the bold text being the ground truth label, so caprese salad. And you can see some of the predictions of the different models, with the length of the bar representing the cosine similarity of the prediction against the ground truth, and the color of the prediction being whether or not Llama considers the total generation as correct or wrong, where red is wrong and blue is correct. So for the first case, you can see that creamy sauce is higher in similarity, but it's considered wrong, while food is lower in similarity, but is considered correct. And indeed, it belongs to the correct but generic type of predictions. You can see also this from a different perspective if you check instead the accuracy for a specific class. So in this case, we get all of the predictions of all the models for all the images of a single class, and we visualize them on a two-dimensional space, where on the x-axis we have the average llama inclusion, and on the y-axis instead we have the average concept similarity. And you can see that roughly on the top right quadrant, we have that Caesar salad and salad are considered correct, while egg salad is slightly less specific. On the bottom right, instead you have more generic but still sort of correct predictions like food, as we saw before. While instead on the left part, you can see what are generally considered wrong. So the top left part is, for instance, pasta salad and shrimp salad, which is specific but wrong, so it's misclassified. And on the bottom left, instead, you have generic and wrong. So maybe the model focus on the bowl or on the plate or last on the fork. And so the first part of the paper is basically evaluating these models and proposing this sort of categorization of the mistakes or of the predictions. Then the second half instead consists of trying to fix these mistakes. Due to time, I will just focus on a couple of these, which specifically focus on the second and third type of predictions, so correct but generic and wrong but specific. But on the paper, you can find even more analysis. The idea would be that, for instance, in the first case, where we have that the prediction is of the model is dog, we may be interested in converting it into Labrador, which may be the ground truth label for the image. In this case, the problem is trying to flip the generic prediction into a more specific one. While for the second case, instead, we would like to address the case where the model misclassifies for instance, the type of cat for another one. So we want to convert a wrong but specific prediction into a correct one. So in this case, for instance, you can think about like Siamese converted into a Persian cat. And for this, we focus mainly on efficient approaches. So like focusing on the prompt, the design. And for the first part, you can see that here for the first two experiments, we ask the models to be more generic or more specific in how it answers the response. And the third visualization is instead about using a fine-grained prompt specific for each of the datasets. Specifically, you can see that for the generic approach, we see that actually the model is very good at making more generic answers. So you can see that we have an increase in all the generic answers, whether correct or wrong. So the light blue and the dark red ones. While for be specific, so asking the model to be more specific in its replies actually never works. It sort of never works, right? Because we have an overall increase in all the wrong predictions, whether specific or generic. Last, using domain-specific prompts, so asking the model, like instead of what type of object is in the image, asking it what type of pet or what type of flower, it's overall very helpful. But also, as you can see that by the boosting, the large improvement of almost 9% on average across all the models and all the data sets, but also results in having an increase in the misclassification problem. Then we propose a similar approach of exploring prompts for the other mistake, so converting wrong but specific into correct generations. And for this, we resort on test time, let's say, test time prompting. So the first one would be zero-shot chain of thought. So we simply ask the model to think step by step before replying. And you can see that it actually works surprisingly well, despite its simplicity. So we get an improvement of almost 10% in total for the correct group of predictions. And instead for the second and third, we resort to more like recent approaches, which the first one consists of doing a multi-turn generation. So we ask to solve the problem by first asking for instance, to describe the content of the image, then reasoning about the problem, and then last proposing a solution. Instead, for the third case, so this one, we just use a more longer and like explanatory instruction for the model, so a longer system prompt, better explaining the prompt and all the steps that the model should go through before answering. And then last, we also explore reasoning models, which are more recent approach, more recent evolutions of large multimodal models that try to sort of let's say, integrate these reasoning, which by, for instance, zero-shot COT or multi-step reasoning and so on, inside of the model. And of course, from here, you can see that generally zero-shot and longer context, longer instructions, it's very helpful, while having a multi-turn may be detrimental. As you can see, we have a huge improvement in mistakes as well. And last, having a reasoning model, which technically should be stronger versions of the models we were testing before, does not actually result in a direct improvement across the entire board. As you can see that we actually get a very huge boost in performance for the correct predictions, correct and specific, but also we get an increase in the misclassification problem. And of course, as I said before, this is only like part of the analysis we did. So if you are interested in like delving in more analysis, for instance, understanding how they work in the multi-label classification and similar stuff, you can just check the work. And here I leave like a couple of links if you are interested.
Yeah, thanks a lot for the introduction of your nice work. So now we can enter the discussion. So if you have any comments, please turn on your microphones and speak. And of course, yeah, usually doesn't work. So maybe we can start some conversation, and then maybe there'll be other people who are joining the conversation as well. So I actually had a question about the CLEAP evaluation. Sorry, for Alessandro. So I think one of the claims that you made was these LMMs are better at open word classification than CLEAPs. Is that the claim that you're making? But yeah, but I'm not sure if that's really. So how do you make this comparable? Because for CLEAP, you said you're using a retrieval-based approach, right? But then for that, I guess you're retrieving the text. Is that right? Based on the image feature. So how do you set the list of possible classes to retrieve?
Okay. Thank you for the question. I mean, like the main claim, I would say it's just, I mean, probably it's twofold. Like one of the reasons why we did this work was also that we got the feeling that people were thinking that the image classification is sort of like dead in a certain sense. So we wanted to give like a new like perspective on this by using more general more like new models and try to solve the problem in a more like real world scenario. So like open world in this case. So not having any priors on the list of candidates for the classification. And I think like the main claim would be that uh, they are good. They are not as good, of course, as clip applied with the list of target labels, which means that there is margin for improvement, right? Because this is like they technically have never been trained specifically for classification, but they still perform okay, considering also that if they not get the exact label or like the very close label, they still may get correct but more generic labels predictions in a certain sense. They, however, are better than taking clip and making it work in image in open world, which was half a part of what we did in one of the works I was referring, like one of the prior works we did, which sort of worked as you said as doing image retrieval. So the naive approach would be you simply have like a web scale image text dataset, so a huge amount of captions from the web, and you just like do retrieval image to text by like clip score, right? By cosine similarity. What we proposed in the other work was sort of similar. It was a similar approach in the sense that it was training free and it was to stage in a certain sense. So it was still doing image to text retrieval, but it was post-processing the captions to extract nouns and then perform basically traditional clip classification. And what we saw there was that at the time, doing this, so like using a clip in this vocabulary-free approach was better than, for instance, blip and lava in doing classification. What we see now in this new setting, which should be noted that has also different metrics because of like requirements from these models, is that actually now these generative models are better than having clip apply for open world. So it's like an in between like clip vocabulary free or open world is a lower bound in a certain sense. Clip closed word is an upper bound that we probably want to surpass. And now these models are in between with different, of course, performance on different domains.
I actually had a question in case, June, if you want to have a follow-up question, go ahead.
No, please go ahead. Yeah, you have more priority.
Okay. Well, about the clip thing as well. So how did you, I guess when we are trying to evaluate these very large multimodal language models, there are many ways in which we can evaluate whether they understand the main content of the image. One of the ways is like what you mentioned, like inclusivity, whether the ground truth class is actually present in like the caption that they produce in a sense. That's one way. But have you, or I mean, if you're either you or some other work that you know of, have tried evaluating them in the same way that we use clip for image classification, where we basically just try to see like the final embedding for the image, what is it more closest to? An image of a and you have like 1,000 class names and just try to see which one is most close to. And does evaluating a model like lava or something like that in that particular way, like the clip way, does it make any difference or should it make any difference? What do you?
Okay, thank you for the question. So I'm not aware of any works that, let's say, treat these generative models as, let's say, dual encoder architecture. So like doing retrieval or like checking, for instance, the like nearest neighbors in the embedding space between image and text. Not familiar in this. I'm like, I think, but I'm not sure. I think it could be that they either perform similar to Clip or worse than Clip. Also because most of these works are based as Clip as a backbone, right? And they remove like the text encoder and just like start from another language decoder only. and they just almost like most of them at the start at least were just learning a linear projection between the two. So it could be that
Okay.
like most of the stuff needed for like doing retrieval or like cosine similarity in the embedding space could be lost. I actually don't know, but
Okay.
practically it's more it's more practical to just do generation in this case, right? I mean, it
So
could be like I'm not saying it's not a bad is a like a bad let's say
yeah,
thing to explore. Probably they could still work. I actually don't know, but it's more practical to just do generation.
but by generation, we generate the actual caption and then see whether maybe the main object class is present in that or
Yeah.
how it's being represented there. Okay. Yeah, no, I think that makes sense from like an average user of LM. They are not going to maybe just check some nearest cosine similarity or something. But I was thinking that if someone has to see that particular ability of these large language models, like what should be the like? Is there some consensus among the community that this is the way that we should evaluate its image classification ability, or is like every paper just tries to come up with their like different way or gives.
So I mean, I don't think there is a consensus on this because like we are proposing sort of this protocol. So I mean, for now, basically, me and my co-authors are the only one that agree on this.
I see.
Uh,
Got it. No, no, it does make sense. Like it's not like, but I was just thinking that since it is such a big, massive system, I can just imagine like many people can just think of all kinds of different ways of evaluating it. So how does one then go about it to establish some sort of standard
I
with
mean,
WM?
I think practically it would still make sense to use sort of this protocol, right? Because as you said, like users just use like ask what's in the image, or
Mhm.
like I mean, and also that's basically the end goal of these models, right? Being used
Yeah.
by like people that are not experts. So just checking like the performance in image classification as they are right now, it's what the end user would get at the end. Then of course, like maybe checking like retrieval in the embedding space between the image and text could give us like a proxy on how they actually reason at a lower level and how if the like can be exploited to improve the performance. Maybe I don't know. Also, for instance, by doing like a RAG in a certain sense, right? You can technically apply RAG to this problem and see
Mhm.
if it improves the performance. Then again, like I think RAG is anyway applied like with specific encoders, right? So it's not like they just use the same language model to do both RAG and the generation. They just use specialized architectures for this. So I feel like in that case as well, we wouldn't actually analyze the performance of these models in this case because they're actually that's not the actual purpose, right? I mean, they're trained for next token prediction. They're not trained
Mhm.
to be like have a joint embedding space for which we can do like geometrical reasoning.
Yeah.
So I have a question for you instead.
Yeah. Yeah. Right.
So I feel like you define some attributes
Yeah.
for the which you can sort of modulate between easy and hard. And
Mhm.
I was thinking that like for a human it may not be so easy to like have a smooth transition between some of the. I mean, yes, you can have sort of a smooth transition between like more or less occluded. But it's like, is it true for like all of the possible properties? Like at least for the ones we identified, I think it was true. But do you think it's like this generalized to like all the possible attributes we can identify, for instance, in an image?
Um. Well, so our the whole so okay the sometimes people can have these questions like how do you define what is easy, what is medium, what is hard? And the reason we went to the attributes is because easy, medium, hard should be anchored along some attribute. Like for example, I think it's if someone says that 2 times 3 is easier than you know some integration equation, yeah, that is true as well. But it is, I think, even more true when someone says 2 times 3 is easier than 2 times 3 times 4. Like we can easily understand that there is a progression along it. So the thing is that since we want to understand the progressive understanding of visual models, we had to go with these attributes. Now coming to your question, whether this progressive understanding is actually possible for all the attributes, uh, I don't think there's ever going to be this objective answer to that. The best, as I said, can be that okay, we show you all the qualitative examples that the model produces, and then humans can kind of judge whether it makes sense or not. So we have done, I don't know if you were there, but we have done some user studies which does correspond to like the correctness of easy, medium, hard across like the 10 different attributes for each different class. Um, but yeah, like it's I don't. This is that avenue where there is going to be some subjectivity involved, and uh, yeah, it just made sense to us and it made sense to the other humans that did the user study. But that's yeah, I don't think one can like guarantee something very strongly. But yeah,
Okay.
so
Then the second question was about a user study, but you already replied that you did
yeah,
one.
the particular way we had done user study was that each user, it will go through many different rounds. In each round, they will see two different images of the same object category, where the difficulty of the same attribute is shifted. So it's again, if you remember the occlusion, they're seeing the easy version of the occlusion, medium version of the occlusion, and then in some other round they're seeing easy and hard version of the occlusion, then medium and hard. So the thing that we then test is throughout all the rounds of the users across all the users, on average, are they actually selecting the more difficult image as indicated by the generative model? Is the human understanding of the more difficult case is matching what the generative model is producing, and it is the case. So that's what we use as like the signal. That it makes sense. So,
And
yeah.
maybe to continue upon the same question, Utkarsh, uh, I've not yet gone through the paper entirely, but in which attribute was there the maximum discrepancy between what the human thinks intuitively and what the model actually thinks intuitively? I mean, in which of the attributes did you find the most discrepancy?
That is a question. I mean, mm, yeah, I'll have to double. I don't think we have that result or in the paper. Like we basically accumulated the result across all the attributes. I don't think we did like the attribute level study whether how much. Let's say if you're saying that for the task for the class of golden retriever, um, there are 10 attributes, right? And then so
Hmm.
for the golden retriever, the agreement of human is like 90%. Now, what I don't think we have done like a piecewise understanding of where different attributes are changing or not. I can check with because that was something that my like co-author had done, but I don't think we had that attribute level breakdown of the overall accuracy in a sense.
Okay.
I had
Bec-
myself also done this user study because, yeah, we are generating the images, but we ourselves have not seen all the images. I don't think for me particularly, like I'd also gone through all the 10 different attributes for different object categories. I don't think there was the case that some attribute was particularly more difficult or it did not make sense. More or less, it was, I think on average, doing something very reasonable. So I don't expect that there will be a lot of variation uh, in a sense. Yeah.
okay. Yeah. I mean, why I asked this question is because I thought uh, an attribute or an addition of complexity like adding an occlusion is kind of more in your face and blatant, but
Mhm.
there are some attributes that are really, fine and
Yeah.
kind of very different in nature from occlusions, right, when compared to occlusions.
Yes. No, that's true.
So
So, uh, and as like, I can just maybe share some more examples of. So for color, if color is an attribute, um, now I think even in this case, like humans can maybe agree that the leftmost one is easiest, medium one, middle one is kind of medium, the last one is like most stylized. Then for texture, we can make it this way. So, um, you're right. In theory, it can be, but yeah, just what we had observed was that, because all of these concerns were something that we had as well, but it just so happened that for most of the cases, the generative model, either the large language model, which is first generating those attributes, and then the image generative model, which is producing images from those things, they were actually doing something somewhat reasonable for a lot of, like in this case, for example, quality. Or maybe this is something that people can doubt that, okay, is the middle one really is the last one really the one more difficult one? But yeah, like this is something that I just, there are some things that we have done to quantify that. So what we have done in the paper is, if you see, sorry,
I understand that this is kind of a foundational study targeting a very open problem. So,
yeah,
of course, I can completely agree that you've not covered every aspect of human understanding in the paper. That's totally understandable. But I was just thinking maybe you already have these results in the paper because I have not yet gone through the paper entirely. So,
no, no, no. No, we like, so we have done attribute level analysis for a different thing, but for human judgment, we basically just report across like different classes what is the agreement rate in a sense, and it's more or less high enough, and that is just the sign that we took that, okay, maybe that plus the qualitative results that we just put out in the papers. Um,
okay.
yeah.
Yeah, in my organization, there are a couple of psychologists working on a railway specific project,
Hmm.
working on human studies of how humans detect objects in a railway perspective and comparing it to object detection models. And
Yeah.
they were trying to compare it with the so-called, concept-based explainability methods. Uh, there's a method that was proposed called craft, I think, concept based refactoring activation or something.
Yeah.
And what it says is, in addition to the conventional saliency map based information on where the model looks at in a particular frame, it also
Hmm.
gives us details on what concepts did the model relate the particular region of the image to. For example, if you're showing a region of the image in which there's a shirt, then the method gives you that, okay, I recognized a shirt in this region of the image, and that's why I decided to classify this region as a shirt. But
Yeah.
then if we compare the model's activity to humans, the humans really can't sometimes understand the concepts as good as the model itself, although in theory the humans are far more intelligent. So
Hmm. I see. Um, So you're saying that just in from that project there was like this discrepancy between how a model is doing things versus how humans are, which where humans are a bit unable to explain or do certain things, whereas the model is. So then
yeah,
what does it mean for something like what we want to do? So,
exactly. I think, of course, there's a huge or a bigger discrepancy between humans themselves. I guess that is
mm,
something that you can't really solve in your study because we're doing
yeah.
like a different side of, we're focusing on a different side of research. But yeah, it would be interesting to see which attributes face the most problems in this
And
comparison.
we can definitely look into that, uh, and refine some of the results. Yeah, I mean, thanks for the session.
But thank you.
Yeah.
Thank you all for joining, and especially thank you, Utkarsh and Alessandro, for presenting your work. It was super interesting, and for the engaging discussion afterwards.
Thank you for
Yeah.
the
No,
invite.
thank you. Yeah, thank you for the invite very much.
Thank you so much, and see you around.
Yeah.
And then we slowly move on to the next session, federated learning.